Thanks very much for coming to tonight's online talk. I'm very excited to present Ben McAllister, who's our speaker for tonight. Ben is a physicist and a science communicator at two centres of excellence, which are big nationwide government-funded research organisations. One is called the Australian Research Council Centre of Excellence for Engineered Quantum Systems, and the other one is called the Australian Research Council Centre of Excellence for Dark Matter Particle Physics. I imagine Ben might talk a little bit more about those and about the research they're doing tonight. He's based at the University of Swinburne in Melbourne, but tonight everyone around Australia is going to get a chance to learn a little bit about quantum and dark matter. And we're doing this as part of the National Quantum and Dark Matter Road Trip. So that's a really fun thing where we have been driving around Australia. We started in Brisbane on Sunday about 10 days ago. We drove from Brisbane through Mount Isa down to Alice and Yulara. It was very exciting to see Uluru. And then we swapped over with the new team and they've gone on to Darwin and then are going on to Broome. We've just got a question. No, I saw a raised hand, but I think it might have been put down again.
Might hold questions at the end.
Yeah. If you do have any questions, if you could use the Q&A feature rather than putting up hands or putting in the chat, that would be excellent because I can monitor them throughout and we'll answer as many as we can. All right. Well, with that, I'll hand over to Ben.
All right, great. Hello. Thanks again for coming, everybody. Thanks to Kristen for that introduction. I am, as you've just heard, Ben McAllister. I'll be talking about some stuff. I'm just going to share my slides now. Cool. Does that look good, visible to everybody? Kristen, you can see that?
I can see that, yes.
Awesome. Fantastic. Okay, great. Yeah, before we begin, though, I would just like to begin by acknowledging the traditional owners of the lands that we're all on tonight. I'm on Wurundjeri country right now here in Melbourne, and pay my respects to elders past and present. Given it is National Science Week, for those of you who aren't aware, I find that it is a particularly cool time of year to acknowledge that Indigenous Australians are some of, if not the first scientists and engineers in the history of the world. So definitely a great time of year to be aware of that and just, pay a little bit of extra respect to those communities. Okay, so who am I? As Kristen said, I am a researcher working with two nationwide research collaborations. One of them is called Equus, which is all about quantum technology, building machines of the future, machines and devices, and I will talk about what that means, what quantum technology is, and what we're trying to do with it. The other is all about dark matter, unlocking one of the biggest mysteries in the universe. What is the nature of this mysterious, invisible stuff called dark matter? And I do work at Swinburne University of Technology. All right. Why am I here? As Kristen mentioned, we have been on the National Quantum and Dark Matter Road Trip. This is the 4th year of this initiative, driving all around different regional and remote parts of Australia, delivering science engagement programs in schools and small communities and town halls and things of that nature. Here is the whole journey. As you can see, it was quite a drive. Kristen and I started in Brisbane last Sunday, drove all the way across down to Alice Springs and then through to Uluru. And yes, as Kristen mentioned, leg 2 began, and they are currently probably here-ish somewhere on their way through to Darwin and then splitting across to head off to Broome. So really cool thing to do in National Science Week or they're around, just get out into some of the communities that don't necessarily get as much STEM engagement. And in addition to that, in addition to driving around and visiting these remote communities, we also do these pop-up events. So things like this that you're attending right now as part of the road trip virtually, and then also events in capital cities. So there are 2 science trivia events in Melbourne in the next couple of weeks. So I'll have some links to some more information about that towards the end of the talk. So that is why we're here. But in the meantime, yes, let's talk about the science. Let's talk about the main reason we're here, which is to learn a little bit about dark matter and quantum technology. So first, I'm going to talk to you about dark matter. This is a picture of a region of space called the Bullet Cluster. It is giant galaxy collisions, many, many galaxies colliding. And the reason that people who talk about dark matter often show this image is because it looks really cool. It's nice to look at. And dark matter is not something you can see. So when we need images, we look for cool stuff in space that sort of has stuff to do with dark matter. And the bullet cluster was a very interesting piece of evidence in the history of the discovery of dark matter. So I'll talk a little bit about that later. That's just sort of by way of introduction. So dark matter, what is the dark matter problem broadly? The dark matter problem refers to something that is huge. It is an enormous problem, and it refers to something of which there is a lot. It is everywhere. In fact, right here, right now on Earth, wherever you are listening, dark matter is passing through you. It's passing through your body, it's passing through the room, it's passing through the planet without really interacting much at all. We know that we have almost no idea what it is. So in a sense, it's a known unknown for us. We know that we don't know what it is. And we know that we can't see it, touch it, feel it, smell it, taste it, interact with it with any of our traditional senses. And just to cap it off, we also know that the vast majority of the universe is made of unknown stuff like this. If we put a pie chart together of all the stuff in the universe, it looks like that, which is to say that the regular matter, which I'll talk about in a minute, which is sort of everything that we understand in the universe, makes up that little purple sliver. And then the dark matter makes up this enormous green sliver compared to the purple sliver. And then there's this huge other big mystery, this big mysterious thing called dark energy, which we know even less about, and which I'm happy to say a little bit about in questions if someone's interested. But suffice to say, most of the stuff in the universe is unknown to us. It is either dark matter or dark energy. And that is a really, really big problem. So when I talk about dark matter, I find it is often helpful to begin talking about what is regular matter. So what is everything that's not dark matter? And regular matter is all the stuff that makes up people and planets and stars and black holes. In a sense, it is everything in the universe that we understand. It's everything that we understand well, everything that we've been studying as scientists for the last couple hundred years. And we've developed a fairly detailed, small-scale understanding of these things. Some of you may have seen this thing. It's called the Standard Model of Particle Physics. If you haven't, don't worry. It is essentially just a list of the fundamental particles that make up all the stuff that we have seen in the universe. So when you take a person or a planet or a star or a black hole and break it down and break it down and break it down and break it down into its smallest constituent components, there are, as far as we have determined, really only 17 things. All of the differences between, the stuff that makes up a person and the stuff that makes up a black hole, it's just different combinations of these things here. In fact, the vast majority of that stuff is made up of just 3 of these things. The 3 in the top left here, the up quark, the down quark, and the electron. They make up most of the stuff in atoms that makes up people and planets and stars. So that is what we've learned. This is the stuff that we understand. That is what we call the regular matter. And with our understanding of that stuff, we can tell a really cool story, which is the story of the entire universe to date. We can say, okay, our current model is that there was a big bang. All of this stuff began in a single point and then expanded rapidly outwards. It was this big soup of high energy, little tiny particles, the things on the previous slide. And then they started combining and eventually grouped up and formed what we call atoms, which are tiny little chunks of matter. Then those atoms clumped up into more complicated things and formed compounds, and then those things eventually clumped together. Well, before that, they clumped together and they formed stars, which ignited in nuclear inferno and then explode and create other kinds of more exotic stuff and scatter all of this exotic stuff across the universe. And that happens for several billion years. And then eventually we end up with rocky planets like Earth, and on that rocky planet, at least one that we know of, things that we call people that are hanging around and wondering about the origins of the universe and looking up into the sky. And that is a really cool story. That's the story of that regular matter that I just described and how it all interacts and groups together. But we know now that that is only a very small part of a much larger story, because whilst all of that was going on, there is 5 times as much dark matter that is there as well, interacting with that stuff and influencing the way that it evolved. And I like to take this opportunity to highlight that dark matter is actually an extraordinarily descriptive name. It's a really, really good name for a thing because it tells you just about everything that we know about it. We know that it is dark, which is to say it is invisible. It doesn't interact with light. And we know that it is matter, which is to say that it has mass. It has some stuff to it. It interacts. It pulls on things via gravity. Okay, so you might be wondering at this point, you're telling me there's this invisible stuff in the universe, it's all around us, it's passing through us, but we can't see it or touch it or feel it. How do we know it's there? Great question to ask. The answer is a couple of different ways, mostly thanks to astronomy. So taking telescopes and looking out in space at the way stuff moves around and drawing conclusions from looking at the way stuff moves around. So the key pieces of evidence are these. I'm not going to go through all of them in detail. They are very Googleable things, though. So if you're interested, I encourage you to look at these things. I will say that that image of the bullet cluster, that's an example of gravitational lensing and how that is evidence for dark matter. So something to look into if you're interested. But I am going to give an example in the form of galactic rotation curves to explain how we know about dark matter. So our planet Earth orbits the sun inside an outer spiral arm of the Milky Way galaxy, which looks something like this galaxy that is on screen. This is Andromeda. This is a nearby galaxy to the Milky Way. And this is a big spiraling thing. It contains big clouds of gas and dust, and they orbit around a supermassive black hole in the center of the galaxy, similar in the Milky Way. And in the 20th century, scientists got interested in studying how these galaxies were spinning, interested in measuring how fast they were spinning and how fast the different parts of them were spinning. And we could look at a galaxy like Andromeda, and we could make a prediction about how we would expect it to behave. And we would expect it to behave something like this. If we just look at Andromeda in this picture here, most of the stuff we can see, the visible matter, is clumped up near the middle. It's really bright there. So there's lots of gas and dust and stars, which means we expect there to be lots of mass there. There's a lot of heavy stuff around the middle part of the galaxy. And then as we get further out, there's less stuff. It's wispier, there's less dense clouds of gas and dust and stars, so we expect there to be less mass out there. And the regions where there are more mass, that means we expect there also to be more gravity. So the reason when you jump on the ground that you do not fly off into space, but you are pulled back towards the Earth is because the Earth is pulling on you with its gravity. Anything that has any mass pulls on anything else that has any mass with gravity, and the more mass you have, the more gravity you have. So that region near the middle of the galaxy, where all the heavy stuff is, we would expect there to be a lot of gravity. And the regions on the outside, where there's not as much stuff, we expect the gravity to be a bit weaker. And so that means if we were going to predict how the galaxy was going to rotate, we would expect the stuff near the middle to be rotating quickly. We would expect it to move around the center quite fast, and the stuff on the outside to move around more slowly. That is because the gravity provides the force that holds the stuff into the galaxy whilst it's spinning. It's like if you've ever had like a ball on a string and you spin it around, you can only spin it so fast before the string breaks and the ball flies off into space. So the gravity is sort of like the string in this context. It's providing the force that holds the galaxy together as it orbits. So where there's lots of gravity, it should be able to orbit quickly, and where there's less gravity, it should be able to orbit slowly. That's our prediction based on what we can see. But when we actually measure these things, what we see time and again, Andromeda, Milky Way, everywhere we look, we see this. The inside spins fast, but the outer parts spin even faster than that. And that is very confusing to us. If we plot it on a graph, it looks like this. So here on this axis, we have how fast parts of the galaxy are moving. And on this axis, we have distance from the center of the galaxy. And this dashed line here is how we would expect the galaxy to spin, how we would expect it to behave. And then this white line here with the real data on it with the error bars is how fast it actually spins. So as you can see, the outer parts of the galaxy are spinning way, 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 way faster than they would if the only stuff providing gravity was the stuff we can see. We can actually visualize this, have this little simulation here, where you can see on the left here, this is how we would expect a galaxy like Milky Way or like Andromeda to spin. The central parts are moving quite fast, the outer parts are moving quite slowly, and then on the right here is what they tend to actually look like. The whole thing is moving quite fast. There's sort of a flat line in velocity as you get further out. So yeah, bit of a discrepancy, quite a big one really, in terms of what we predict a galaxy to behave like and what the galaxy actually behaves like. Given it is National Science Week, just a quick shout out to Vera Rubin, the woman who largely pioneered and discovered this effect in the 1960s and 1970s. So yeah, National Science Week, props to Vera Rubin. Okay, so I'll highlight, this is just one example. I mean, as I said, there are two other things here and some other bits of evidence that look kind of similar. Essentially, we're seeing weird things where things in space are not moving the way that we would expect. So what's going on? Well, there's two hypotheses or theories, if you like, in the common term that you can form. One is that gravity is just wrong. We just don't understand gravity. And that's definitely something that you can say, and it's definitely something that people believe in some circles, and it's definitely something that is it's fair to call active research. Like that is a hypothesis that scientists are working on, is that there is a different theory of gravity that could describe these same effects. There are a few issues, though. One is that gravity, our regular theory of gravity, general relativity, is really, 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 really good in a lot of contexts. It's really, really precise. It's one of the most well-tested theories ever. So we have a lot of reason to believe that it's not completely wrong, and we just need to completely discard it. And the bigger problem is that nobody has come up with a theory of gravity that works. No one has been able to say, okay, here's how you change gravity and explain this dark matter stuff. It just hasn't been done yet. So it's definitely something that people think about, but it is not the preferred hypothesis at the moment. The preferred hypothesis to explain what these weird effects are is that there's just some other stuff in the universe than this. I mentioned these 17 particles before. Maybe there's just some other stuff in addition to those that is providing extra mass, that provides extra gravity, and makes galaxies and other things move the way that they do. And if you ask me, that shouldn't actually strike us as all that weird. It wasn't that long ago, only about 10 years, that we discovered the last one of these things on the diagram, the Higgs boson. It would be awfully bold of us to assume that we've now discovered everything that there is in the universe. Why would it be the case? So why would it be so surprising that in addition to these things, there is some extra stuff out there that we don't know about yet? Personally, I don't find that hard to believe. And what that would look like is that maybe in addition to this table here of our standard model of elementary particles, there's other stuff that sits alongside it that we call dark matter. Maybe a thing called a WIMP, maybe a thing called an axion, maybe some other stuff altogether. These are different candidates to exist in this space, things that might make up the dark matter. And we'll talk a little bit about these two things in a minute. So when we're thinking about dark matter and candidates to be dark matter, things that can explain these weird effects, there are one helpful way to think about it is to think about it in terms of the 4 fundamental forces. You may have heard of these. If you haven't, that is okay. The fundamental forces are a list of all of the things that we know that are allowed to happen in the universe. And in a sense, we don't have like any reason to think that there's only 4. We don't know why any of these things are in our universe. It's really like observational. We have seen these 4 things occur. And so far, everything that we have ever observed, we can describe in some combination of these 4 effects. So electromagnetism, if you've ever held 2 magnets together and felt them either attract or repel, that's electromagnetism. It's also why static electricity behaves the way it does. Like charges repel like charges and opposites attract. Gravity, we've talked a bit about gravity before. That's the force where anything that has any mass is attracted to anything else that has any mass. You are attracted to the Earth is attracted to you. The strong and weak nuclear interactions relate to stuff that goes on inside atoms. They happen over very, very small length scales, and they're not too important for us today, so we're not going to think about them too much. Interestingly enough, electromagnetism is actually the main force that you experience in your day-to-day life. People often think that it's gravity that they feel, but what you actually feel is electromagnetism. So if you put your hand down on the table in front of you, or when you're sitting in the chair that you're in, the reason that your hand doesn't pass through the table or that you don't fall through the chair that you're sitting in is because the particles in your body and the particles in the table or the chair are repelling each other via electromagnetism. That same force that keeps 2 magnets, north poles, from coming close together is repelling the particles in your body from the particles in the chair or the table. So you are supported on a cloud of electromagnetism. It's the thing that keeps collisions from occurring like that. So what we know about dark matter is that it can't experience electromagnetism because it passes right through things without having collisions. It must experience gravity because that's the only way we know about it. It can't experience the strong nuclear interaction because if it did, it would mess up the way that atoms form and we would have detected it by now. And we're not sure about the weak nuclear interaction. We don't know whether it experiences that effect. Another reason we know it doesn't experience electromagnetism, by the way, not just because of its collisionless nature, but also because of the fact that we can't see it. So it turns out that everything that experiences the electromagnetic interaction interacts with light. That's just one of the things we know about it. Anything that can have that push effect of like charges repelling like charges can also have light bounce off it. So it's deeply connected, the fact that we can't see the dark matter and the fact that it passes right through us. So in a sense, that makes sense. Us not being able to see it also means we expect it to pass right through without us touching it. Okay, so when we look at these things, when we look at these effects, these things that we know dark matter can and can't do, we can say that we expect we can start to build up some hypotheses for what dark matter might be. And there are two really popular ones. One of them is a particle called a WIMP, a weakly interacting massive particle. Yes, we're aware that's a funny acronym. Funny acronyms are very important in particle physics in particular, as you will learn later. And axions, a name of another type of particle that might explain the dark matter. So two hypothetical particles that we aim to search for in experiments in Australia to explain what's going on. So I've mentioned that we search for these things with experiments. How do we do that? What do those experiments look like? What kind of experiments are we doing? We are doing direct detection experiments. So trying to capture the dark matter directly. So right now, we only know about the dark matter indirectly. We've only seen its effects on stuff we can see. We can't see the dark matter. We can see it pulling on things we can see. That's what we call indirect evidence. So it remains essentially a hypothesis that this stuff is responsible for what's going on in the universe. So we need to do direct detection, detect the dark matter in some other way to confirm that we understand what's going on. So we try to build these detectors. And it's important to remember that dark matter is all around us. It is not just out in space. We don't have to get up in spaceships and go out in space to find this stuff. We can build our detectors here on Earth, and the dark matter passes right on by, and we can detect the dark matter as it passes through us. We can try and understand it whilst it maybe interacts weakly with some material inside our detector and gives it a little bit of extra energy. So that's what it boils down to with this direct detection. There's a wind of dark matter passing through us, and we essentially want to harness a little bit of the energy of that wind by it interacting weakly with some of the stuff in our experiment. And in Australia, there are two main experiments that do this right now. One of them is called SABRE, and one of them is called ORGAN. Remember, I said before that silly acronyms are very, very important in particle physics, especially. Okay, so what are these two experiments? What is SABRE? What is ORGAN? SABRE looks like this roughly. It is a tank containing some special stuff. So in this tank here, we have a variety of different things. In the middle here, you'll see there are these copper enclosures, and those copper enclosures contain special crystals called sodium iodide crystals. And the idea is that if dark matter is made of one of those two candidates, the thing we call the WIMP, that it might bump into one of those crystals and give the crystal a little bit of energy. And this is a special crystal. It's a type of crystal called a scintillator, which is just the name of a certain class or variety of crystal. And when it is given a little bit of energy by a particle bumping into it, it emits that energy as a little flash of light. Tiny little flash of light comes out of this crystal, and then it is detected by photodetectors. That's these things around the outside here, other things on the crystal chambers themselves, looking for these flashes of light that occur inside the crystal. That is effectively the core idea behind SABRE. It's this tank contains these crystals and looks for little flashes of light when dark matter bumps into them. SABRE is located, or will be located, deep underground in Stawell in regional Victoria. So if you drive northwest of Melbourne, you will eventually find yourself in a little town called Stawell. And there in Stawell is a functional gold mine, Stawell Gold Mine. It is the Stawell Gold Mine. It is still operational. And 1,024 meters underground, inside the Stawell Gold Mine, is the Stawell Underground Physics Laboratory, where SABRE, this dark matter detector, is being built. And the reason that this experiment has to go deep, deep underground is because here on the surface of the Earth, where I assume everybody listening is right now, we are constantly being bombarded by what are called cosmic rays, high energy particles from space that hit the Earth's atmosphere and generate showers of these things called muons that interact in our detector in a way that is similar to a dark matter signal. So if we built SABRE on the surface of the Earth, it would constantly be being bombarded by these high energy particles, and we would have no chance of observing the tiny little effect of dark matter, because it would just be washed out in the noise from all of these high energy particles from space that interact in a similar kind of way. So SABRE being built deep underground, looking for WIMP dark matter in Victoria. I also want to talk about another experiment that exists in Australia, which is called the ORGAN experiment. The ORGAN experiment, again, acronyms, very important in particle physics. So here's a picture of the ORGAN experiment on the right here. All of this gold stuff is kind of life support for the interesting part of the detector, which is this red circled thing down here. Again, this little copper cylindrical structure. And the key idea behind organ, at its core, is really kind of similar to Sabre, even though many aspects of the experiment are quite different. The key idea is that this time axions are our dark matter, and they enter our detector, this little copper thing down here, and they interact, this time not with the crystals, but with a strong magnetic field that we apply. So this whole thing sits inside a really strong magnet. The axions interact with that magnet and then generate a little flash of light. So again, we're taking dark matter, this thing that we can't see, and converting it into a little flash of light that we can then measure using some sensors. So again, here's our detector, axions come in, boom, little flash of light, and there are some sensors attached to this chamber that we can then try and read out the light. A little bit more about organ. It consists of something called a resonant cavity. So that is what this chamber is here. It's sort of like a flute or like a woodwind instrument where you will have noticed, if you've ever played one of these things, that there are certain frequencies of sound that will vibrate inside the tube when you hit a resonant frequency of your flute or your woodwind instrument. It's a similar concept here. This little cavity has certain frequencies of electromagnetic radiation that will resonate inside it. So the resonant cavity is there to trap the light that is generated and cause it to bounce around, essentially. Trap the little flashes of light and have them bounce around inside it. Then it is cooled to very low temperatures. And the reason that it is cooled to low temperatures is the same reason that Sabre goes underground, and that is about background noise. So if you have ever seen a thermal imaging camera, like this image here, then you know that anything that has any temperature is constantly emitting a small amount of light. It's not necessarily light that we can see with our eyes. It's infrared radiation or even lower energy than that. And that would essentially completely destroy our chances of ever seeing the dark matter signal generated by axion dark matter, because it provides background light that would interfere with our senses. So we cool these things down to very low temperatures. And when I say low, I mean like negative 273 degrees, a few thousandths of a degree above absolute zero, the coldest possible temperature. And that is what all of this gold stuff is. That's what I mean by life support. This is a thing called a dilution refrigerator, a very important piece of technology that physicists have developed, both to do experiments like this and also for other applications in quantum technologies that I'll talk about a little bit later, amongst other things. So, okay, we've got the resonant cavity, we've got it cold. We also, I mentioned before, need to submerge the thing in a big, strong magnet, because the magnet is the thing that forces the axions to convert into photons if they are there inside the detector. And when I say strong, I mean really strong, like stronger than a magnet that runs an MRI machine, stronger even than like a magnet that would be used in a scrapyard to pick up a car. So very strong magnet, very custom-made strong magnets for these purposes. And organ is currently operational at the University of Western Australia. So out on the other side of the country, axion dark matter research is going on. So those are Australia's two current contributions to dark matter detection research. And now I would like to talk to you a little bit about quantum technology before I come back and talk about how these things are related and how they're connected. So quantum. What is quantum? It's kind of a buzzword. You may have heard quantum get thrown around here and there. It gets used in science fiction a lot. It gets used in products. There are a lot of products that will tell you that they're quantum now. Quantum dish soap, quantum washing detergents, things of that nature. One place it comes up is in places like the Avengers movies or Marvel movies in general, where you'll hear concepts like nanotechnology and Planck lengths and the quantum realm. And these are all based on real science things. These are real physical concepts. The way that they're represented in the films is not necessarily always accurate, but that's just fine. I mean, I'm personally, as a physicist, I don't need my science fiction to be super accurate. I think you can enjoy it just for what it is. But I just think it's cool to highlight that, yeah, at least these are real things. So what is quantum? When I am talking about quantum, much in the same way as with dark matter, I find it helpful first to talk about what is not dark matter. I find it helpful to talk about what is not quantum. So when we talk about quantum physics as physicists, we are talking about it in contrast to this thing called classical physics, which is all of the physics of our intuition. It's all of the physics of the everyday world. It's things that are large scale. And when I say large scale, I do mean a solar system and planets orbiting it, but I also mean like a guy on a motorbike, and we also mean like a tennis ball. Essentially anything you can touch, with your hands and see with your eyes, you can use classical physics to describe the way that it behaves. And classical physics is the stuff that you will have learned if you have done physics or science at school. You will have learned about like Newton's laws of motion. If you haven't, that's fine, but it's just essentially all of the stuff that we've understood for a couple hundred years now of the way that big things move around. An example of this is like Hawkeye in the tennis. If we know all of the information about a tennis ball, we can calculate using physical laws how that tennis ball is going to behave. The analogy I like to give is actually, let's say you took a tennis ball and you threw it across the room, and you told me everything about the tennis ball. You told me the fuzz, the density of the fuzz on the surface. You told me how fast it was traveling. You told me the air density in the room. You told me the direction it was thrown in. You would be able to calculate with certainty where that tennis ball was going to land. And if you threw it 100 times, it would land in the same place every single time. So that's what we mean when we say classical physics is predictable and repeatable. We can predict what's going to happen, and it repeats the same way every time. But it turns out when we get down to what we call quantum scales, things that are very, very, very small. And when I say very, very small, I don't mean a grain of sand. I mean a lot smaller than that. A grain of sand is still a classical object. If you threw it, you would still calculate where it was going to travel. We're talking much, 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 much smaller. Down into the realm of those individual particles that I was talking about when I was talking about dark matter before, into the world of those tiny little chunks of matter that make up everything. Something like an electron, which is a thing that goes inside an atom, is a great example. And you can see here, I mean, I don't know how many zeros that is. It's many, many, many times smaller than a grain of sand. When you get down into that length scale, all of that physics that we have intuition for, that classical physics, breaks down and we enter the realm of quantum physics. So quantum physics relates to things that are small scale, and it is inherently probabilistic and unpredictable in contrast to classical physics. So the analogy I like to give here is that if I took an atom and I threw that across the room, it doesn't matter how much information you have about the atom. It doesn't matter if you know how fast it's going, the direction it's going, everything about the room. It turns out that you cannot predict with certainty where the atom is going to land. You can predict where it's likely to land. And that's what we mean by probabilistic. You can say, okay, it's most likely to go here, but there's some probability that it would go here or here or here or here in this smeared out region of space. And if you throw it 100 times, it doesn't have to land in the same place every time. It's going to land with a probability distribution somewhere within that region. Most of the time, on average, it's going to land where you think it's most likely to land. But some of the time, it's going to land in different areas. It's going to land in outlier spaces. So that's what we mean by it being probabilistic and unpredictable. On small scales, the universe is just inherently a bit smudgier. It's a bit wavier. And that's what's represented in these pictures here. So electrons, when they orbit around atoms, don't actually have well-defined positions like they do in this sort of cartoon image here. They're actually kind of smeared out in space in these probability clouds, as they are known. Okay, so that's the core idea. The universe is a bit weird on small scales. Why do we call it quantum? It's for a very boring reason, I'm afraid, and that is Latin. Quantum is another word for discrete. So I'll talk through what I mean by that. In the world, we know that things can be either continuous. And when I say continuous, an example of that is like a mass on a pulley here and being asked, how high can the mass be off the ground? The answer is it can be wherever you like. It can be at point A or point B, or anywhere in between point A and point B. It exists in a continuum, a continuous range of states. The mass can be by just moving the rope here and pulling it over the pulley a little bit, you can essentially put the mass wherever you like. That's an example of something that is continuous. An example of something that is discrete is like a mass on stairs here. So if I say on the right, where can the mass be? It can only either be on step 1 or step 2 or step 3. It can't be anywhere in between. So that is what we would call something that is discrete. And a Latin word for discrete is quantized. So effectively, quantum just means discrete. It means that things are in specific states, like this or this or this, but not anything in between. And I can give an example of why the world behaves that way with a piece of rope. Unfortunately, none of you are here to help me move an actual piece of rope around, so I have to use a simulated piece of rope. So here we have a simulation of what happens if I just wiggle like a little piston here that moves this rope around and the other end of it is clamped. So as you can see, if I drive it at just some random state, then it doesn't do much at all, really. But if instead I drive it at specific frequencies, if I drive it in the right way, I can get this rope to form stable states. So if we wait a minute, we'll see a nice stable oscillation on this rope here. If you've ever swung a skipping rope around, you've probably seen something quite like this yourself, where the rope has, a nice wave structure that oscillates from a peak to a valley, and it's nice and stable. And then if I try and drive it somewhere else, if I first kind of stop it and then try to drive it in some other way, you'll see, yeah, it doesn't really exist in a stable state like that. The rope doesn't really wiggle as much. It kind of looks a little bit unstable. But if I move it up to another position and then start it again, we can see that it enters a state that is kind of similar to our original state, except now, instead of there being just one loop, one peak, one valley, there are two. We've got this resonant wave on a string where there's one peak, one valley, one peak, one valley on the other side. And we can keep going up like this to higher and higher frequencies and find that there will eventually be a state, if I keep going for a while, where now there are three of these things. And you can see that there are these sort of nearly fixed points on the rope that don't really move, and these three peaks and three valleys on the rope. And if I keep going up and up and up, this will continue to occur. So what we've seen here is that when we have a string that has a wave on it, or when we have a wave in general, it can exist in these kind of fixed states where there's either one or two or three lobes on the wave. But if I try and put anything in between, it doesn't really work. Nothing really happens. The rope doesn't really move very well. And it turns out that that is deeply related to why quantum physics is the way that it is. Those wave states that we were just looking at in the last simulation are very closely linked to energy states in quantum systems, because quantum particles have this thing called wave-particle duality. It turns out a particle, like an electron or one of those other things that I was describing before, doesn't really exist. It isn't really a particle. It is simultaneously a wave and a particle at the same time. So waves and particles being the same thing at the same time is one of the fundamental principles of quantum mechanics. And it leads to all kinds of physical phenomena. If you've ever heard of the energy levels in an atom, the reason that those energy levels exist is because the electrons are fundamentally wave-like. Which leads to the emission spectra of a hydrogen lamp and all kinds of things. If that stuff is a little bit out of your understanding of physics, fair enough. It also led to all of the technology that we have today. So it turns out if you want to build really, really small computer chips, like the ones that go into phones or computers these days, when you're down on those small scales, if you don't understand the wave-particle dual nature of the particles on those scales, you can't engineer them. So all of our work in semiconductors, all of our work in lasers, all of our work in things like solar cells is all based on our understanding of quantum physics. It's all based on an understanding of that wave-particle duality, the fundamental waviness and uncertainty associated with physical systems in our universe on small scales. And yeah, that understanding was responsible for what we now call the first quantum revolution, which was the technological revolution of the 20th century that brought us the entire modern world. But it turns out that wave-particle duality is only one of the weird things about quantum physics. There are other concepts that also happen on these small scales that aren't just the fact that things are fundamentally wavy. There's a thing called superposition, and there's a thing called entanglement. And the research that's going on now in Australia is to try and take advantage of some of these phenomena in the same way as we took advantage of wave-particle duality to engineer new technologies for the second quantum revolution. So I can give you some analogies to describe what these things are: superposition and entanglement. Okay, let's talk about superposition. So if we imagine, again, to just go back to our classical world, imagine I had a coin. Classically, that coin can exist in two discrete states. So it can either be heads or it can be tails. If that coin was a quantum system, though, if it was so small that quantum mechanics started to take hold, it could exist in a third thing called a superposition, which is kind of like a spinning coin. It's kind of like it being both heads and tails simultaneously. And again, I want to stress this is an analogy. Obviously, in reality, this isn't something that happens to coins. Coins are far too big to exist in quantum states. But very, very small particles like electrons can exist in superpositions of one state and another state at the same time in something like a spinning coin, something like being in two states at the same time. And the analogy goes a little bit further, because if we ever wanted to say we had our quantum system, our electron, and it was in a superposition of two states at the same time, if we ever tried to measure it, if we ever wanted to look at what that electron was doing, it is like stopping our coin spinning. We have to stop it spinning to measure whether it is in one state or another, and that destroys our superposition. So superpositions can exist, but they are inherently quite fragile. Anytime you measure them, they just collapse. And it's not just measurement that collapses them. The biggest challenge in actually building useful things out of quantum systems these days is decoherence. There's a little analogy for that here. It's like if you spin the coin and it just gradually falls out of superposition on its own from interactions with the environment. So these quantum systems are inherently quite fragile. We can prepare them. We can say, okay, this electron is now in two states, or it's in a superposition of states, but it will eventually lose its superposition over time because of what we call decoherence, just the natural loss of quantum systems. So we'll talk a little bit about that fragility in a moment. Let's talk quickly about entanglement, which is another weird quantum phenomenon. So a classical analogy for entanglement is a situation like this, where we have some prior knowledge of a system. So I have a bag and I know it contains a green and a blue ball. If you then draw one of the balls out and you see that it is green, then you know that the other one bag is blue. And that's not mysterious. That's a correlation that occurred because of prior knowledge. And that's a classical system. In quantum mechanics, something different can happen, which is, again, let's imagine we have our quantum system in some kind of superposition, which is represented by our spinning coin here. And let's imagine we have two of them. When these systems are entangled, we can leave them in a superposition state. We can separate them. We can put one on the other side of the universe. We can move them as far apart from each other as we like. As long as these states retain what is called quantum entanglement, if I measure this one over here and collapse it into one state, the other one instantaneously collapses into a corresponding state regardless of distance. There is some information transfer between the system on the left and the system on the right because of this bizarre thing called quantum entanglement. And that is fundamentally different to the classical example that we had before. Because it's not just that these particles were actually always in, this one was in this state and this one was in the other state. And when we measure this one, we know what the other one is. We can prove that these things are actually in these superposition states when they are prepared and separated. And it is not until you measure them that you destroy that superposition and force the other one to be into the corresponding state. So that's entanglement. It's really weird. We don't have intuition for it. It doesn't make sense. It's just something that we know is true and that we can describe mathematically, but it's not something that we can really wrap our minds around intuitively. And with that, I'd like to talk a little bit about quantum technology and what we hope to do in the second quantum revolution. So I mentioned using superposition and entanglement to build new kinds of technologies. And there's three classes of quantum technology that we're building at the moment: quantum sensing devices, which exist now, quantum communication devices, which will be coming soon, and quantum computing devices, which will come at some time in the future. Okay, so what is quantum sensing? Quantum sensing is essentially taking advantage of the fragility of those quantum systems that I described before to enhance the sensitivity of different kinds of measurement devices. So this is done in biology and medicine. You can see the enhancement that has come from MRIs in the last 20 years or so from using quantum technologies. There's so much more resolution than we have on brain scanning. This is an example of using a microscope to look inside a cell. You can see using quantum sensing, quantum enhanced microscopes, we are able to get more resolution on what's going on inside these cells and have clearer images. It can also be used to enhance LiDAR and sensing of autonomous vehicles. It's being used in satellites to do very precise gravitational measurements and timing measurements. It's also being used as sensors for dark matter. So this organ experiment that I showed before has some quantum sensing devices built into it. I'll talk a little bit more about that a little bit later. Quantum communication is sort of technology that is being developed right now that's sort of near to being useful. So the idea is that quantum communication can be both much denser. We can pack many more bits of information into the same physical process by making use of superpositions. So that's what's represented in these smudgy images here. You could imagine building up an alphabet with different states of light, where a different state of light is a different letter, and then creating a superposition. Here we've used E, Q, U, and S states of light to generate the word equus, all encoded in a single bit. So taking advantage of superposition, we can make much denser information. Or quantum communication can also be incredibly secure, using that weird process of entanglement where information between two different states seems to be shared in some way. You can start to imagine using that to take advantage of that phenomenon to transmit information, or at the very least, prepare information in one state and know what information is somewhere else. So this is being used to generate very, very secure, unhackable communication networks. So this is stuff that is sort of research and development that's happening right now. And in the future, we hope to develop computers that are based on these quantum principles. So a standard computer exists using things called bits, which can either be in a 0 or a 1. If you've ever heard of binary code, that's what that is. Your computer is essentially a series of tiny little things that are either on or off, 0 or 1. But in quantum computing, if we encoded that same information into quantum states, then they could be in superpositions of 0 and 1 at the same time. And you could do different kinds of computations by using those quantum bits, things we call qubits, instead of regular bits. So these are just some examples. These are some qubits on a chip here. This stuff is a little bit further away, but quantum computing is exciting because quantum computers, we know, we can predict that if we could build them, they could do kinds of calculations that we can't do with regular computers. So it turns out trying to simulate and model quantum systems, things like chemistry, things like biology, very, very small structures, is really, really hard to do with a regular computer. And we just can't model them that well. But if we had a quantum computer, we know that those calculations would be easier, and we'd be able to model things like medicines and pharmaceuticals much more precisely. We'd be able to model things like fertilizers for more sustainable farming practices or agriculture practices. We'd be able to make more secure encryption. We'd be able to do all kinds of interesting computations that we just can't do with regular kinds of computers right now. So that stuff's a little bit further away, but it is very exciting in so many areas that there is a lot of investment around the world being poured into it. Examples include a few years ago, CSIRO, the peak science body in Australia, released this report, their quantum roadmap, where they said by 2040, we're going to have $4 billion and 16,000 new jobs in Australia in all of these industries with quantum technology. This was only a few years ago in 2020, and it has already been massively surpassed. More recently, 2023, the government published its national quantum strategy, where they identified the requirement to build a skilled and growing quantum workforce because they saw that this wave of quantum technology was coming much sooner than previously thought. And they are now thinking by 2030, 1.2 million technology jobs. Basically, any job that is in advanced technology is going to be in some way impacted by these coming quantum technologies, communication, sensing, possibly computing. And there's a lot of money pouring into it. This is the investment just in the last couple of years in quantum technology in Australia. And yeah, we'd just like to highlight 2025, International Year of Quantum Science and Technology. So keep your eyes peeled for more events and stuff to do with that. Okay, so how does quantum help dark matter? Why do the Dark Matter Center and Equus hang out and do these kinds of outreach things together? Well, it's pretty simple, actually. If you want to measure something very, very tiny, a quantum signal, a little tiny individual flash of light, you need a very, very precise sensor, or a quantum sensor. So both of the dark matter experiments I described before are looking for individual little flashes of light, tiny, tiny chunks of light that are called photons, single particles of light. And the smallest signal you can possibly detect is one photon. And to detect a single photon, if one of these dark matter experiments generated a single flash of light, you need a quantum device. In other words, you could imagine getting our dark matter detector and putting a classical photon sensor, which is basically just a camera, and a quantum photon sensor, represented here by our spinning coin, and then introducing a single flash of light to them. If you introduce the single flash of light to a regular camera, like a single photon hitting just a standard camera, it's not going to be bothered. They don't have that kind of sensitivity to pick up individual photons. But we were talking before about how delicate and fragile quantum systems are. And if you, in some cases, shine a single flash of light at one of these systems, you collapse the superposition. And that is something we can measure. So by using quantum technologies, we can massively enhance our searches for fundamental particles, particle physics in general. You might be wondering, okay, cool. I can see quantum technology. I can see how it's related to dark matter. Why do we care about dark matter at all, though? That is a fair enough question to ask. And I think that the answers are, well, there are a few. I mean, there's it's kind of a lofty answer, which is that like it's just such a giant mystery, and it's our natural human curiosity to explore and try and understand the universe. And this is most of the universe. It's this gigantic, gigantic mystery. So how can we not want to figure it out? But I think there's also a more practical answer, which is look around at the modern world and look at everything that has ever been invented: computers, modern medicine, space travel, all of art and literature, everything that has ever impacted your life in any way, and understand that all of that was done with an understanding of just that little 5% of the universe that we do understand. And there's 5 times as much again in this stuff called dark matter, and we have no idea what it is. So in my view, we just need to figure that out first, see what it is, and then I mean it would be weird if it wasn't useful for something. So that's a sort of a slightly more pragmatic answer, but I could talk about that all day. So with that, I will wrap up and I will take questions. Thank you for listening.
Thanks, Ben. That was excellent. We already have a couple of questions.
Great.
So the first one is, when you talked about the experiments and how they emit little lights or just photons, how do you detect the light with sensors if there is light in the room?
Yeah, that's a great question. So the answer is different ways. So I'll just stop sharing screen for now, I guess, so people can see my face. Hello. So I talked before, when I was talking about organ, about how everything is emitting light, but it's not necessarily light we can see. And that is because light exists on a very broad spectrum. So the same thing that makes an X-ray that is used in like medical imaging is actually the same thing as a radio wave. They're both light. They're just light of different wavelength, or light of different energy, if you like. And now light sensors are only sensitive to specific radiation bands at any given time. So the light that Sabre is looking for is not the same light that Organ is looking for, which is why their backgrounds are different. Sabre is looking for optical light, stuff that is similar to light we can see. Organ is looking for microwave light, so much, much lower energy light. That's not the answer to your question, though. The actual answer to your question is that shielding that light is like one of the most important things that is done. So Sabre exists in this big dark tank that shields the light from the rest of the room. And it's very dark in there, and background light is actually one of the dominant backgrounds. And in the same way as going underground to shield from cosmic rays, they also need to keep stray light sources out. And with Organ, so the picture that I showed of the dilution refrigerator has all of its radiation shielding off, so you can see what's inside. It sits inside some big cans that screen all of the light in the room out, and then the signals are read out through data cables that run through those shields. So yes, keeping the light background down, very, very, very important. And it's done in different ways. Cooling is one of them because it keeps the thermal light from interfering.
Okay, another question. It is said that dark matter doesn't interact with matter. Then how do you detect it?
Yeah, right. Great question again. So I guess what we say is that we expect it to interact kind of weakly in different ways. So it's like, in order to detect dark matter, you have to have an idea of what it is. And so that's why, like, when I was describing the candidates, I talked about just 2 of them. There are many, many more, but 2 of the very popular ones are WIMP dark matter and axion dark matter. And these are both models of new particles, and they just interact very weakly with our detectors. They interact in specific ways. So in the case of WIMP dark matter, the model predicts that it should interact by the thing called nuclear recoil. So very occasionally, a WIMP particle might bump into the nucleus of an atom and give it a little bit of energy. It's a very rare effect, so it's not something that happens so much that we would expect to have observed it without trying. And that's why we need to build these experiments, because we're looking for these very, very rare nuclear recoils. And that's why we say it doesn't interact, because it effectively doesn't interact. It only interacts very, very weakly. And with axions, it's this very weak coupling to photons, where they generate these little flashes of light. Of course, both of those models could be wrong. Dark matter could be something else entirely. And if it is not one of those things, then it wouldn't interact in those 2 ways. So that's why we build multiple different experiments. So we say, okay, we're not going to put all our eggs in one basket and say it's definitely this or it's definitely that. We're going to pursue a wide range of options. And if it turns out that dark matter is something more exotic that doesn't interact in those ways, it doesn't interact with nuclear recoil, or it doesn't interact with light in the way that we expect axions to, then we wouldn't see it with those experiments, and we might never see it. If it truly is just some exotic particle that only interacts gravitationally, the only thing it does is have mass and pull on stuff we can't see, it would be very hard to detect that particle. And like, there's no reason that the universe has to make these particles detectable for us. It could just turn out that we can't observe them using those kinds of experiments, but we won't know that until we try. And we have to assume something in order to build a detector. So that's essentially the name of the game. We say, big problem. What are our best hypotheses? What are our best guesses? And these guesses are not random. The particles like the WIMP and the axion, they don't come from nowhere. They come from other good theories that predict that they exist. And yeah, but you can't play favorites. Like, if you build the experiment and you don't see the thing, you have to move on to the next candidate. And that's science. You do it wrong a lot of times until somebody does it right. So that's the name of the whole endeavor.
And sorry, that was a question from Hinza. And just to clarify, so when you say weakly interact, you mean via the weak interaction that had the question mark on it, or do you mean something else?
Both things. I mean both things. So it might be that it interacts via the weak interaction, one of the four fundamental interactions. It might also be, in the context of axions, well, they also can do that, that it just has another weak an interaction that is weak in nature. It is of low strength. So yeah, it can mean different things kind of depending on the specific context of the particle that you're talking about.
Okay. So there's a question here from Mark. Earlier, you said that everything that experiences electromagnetism has to interact with light. So does air experience electromagnetism?
Yeah, it definitely does. So air is a combination of different stuff. In the air, there's oxygen and nitrogen and carbon dioxide, and all of those things experience electromagnetism. They just don't, like the little molecules of air in the room, they will absorb light if a light hits an oxygen molecule, and it doesn't absorb all the light. So that's why you can see. So there's like so much light coming out, like so many photons coming out of the light on your ceiling. Some of them will be absorbed by matter that's in the room, and some of them won't be. But yeah, air, the stuff that is inside air definitely experiences electromagnetism. That's why air molecules form. That's why oxygen molecules form, and they hold tight to each other using electromagnetism. So yes, 100%.
Next question. Would dark matter behave like normal matter in the sense of a corresponding antiparticle?
Yeah, so this is where we get into the realm of maybe. We don't know. So it depends what it is. Some particles do and don't. Some models of dark matter do and don't have antiparticles. So it kind of depends on what the dark matter turns out to be, unfortunately, is the best answer I can give you.
So then there's two related to dark energy. So what is dark energy?
Yep.
And will dark matter tell us more about dark energy?
Yeah, sure. So dark energy, I will caveat this answer by saying it is not one of my research areas. So I am by no means an expert, but I will say that what we know about dark energy is very little. It's a big mystery. What we know that it does is drive, or what the models that we have at the moment of dark energy predict that it does is drive the expansion of the universe. So we know that the universe is constantly expanding, and dark matter acts kind of as glue that pulls stuff in the universe together because it's heavy. It's most of the mass. So like, of the 30% of the universe that is matter, most of it is dark matter. And so dark matter is like stuff that pulls things in. It binds galaxies together, and dark energy seems to kind of do the opposite effect and push the universe apart. But we don't really know what the dark energy is made of, or like anything really. So it's a big mystery. So we can sort of characterize how much of it there is by modeling the way the universe is expanding and the way that the early universe formed, but we don't know what it's made of.
And would dark matter tell us more about dark energy?
Yeah. So again, when we're maybe again, like a lot of these answers are kind of unsatisfying because dark matter itself is such a big mystery, that it kind of depends again. So it depends what the dark matter is. I think like it definitely wouldn't hurt understanding, like, whatever we discover dark matter to be, it will be a big paradigm shift in physics. It will tell us something new. It will blow a hole in the standard model, and it will certainly open further questions. Like if we discover axions or WIMPs, then that will create new areas of physics studying those things and will open new lines of inquiry. And that will possibly lead to answers about dark energy. So any new discovery of a new particle or something like that can't hurt in terms of trying to answer these big mysteries.
So there's one a bit about quantum, and then there's a few more, or many more at the moment, about various theories. So just jumping to the quantum one, what will the federal government's investment in building a quantum computer in Brisbane do to the established Quantum Research Centre in Sydney?
Hey, that is a good question, and not one I feel especially equipped to answer, not being one of the people involved in the Quantum Research Centre in Sydney. I guess the optimist in me would like to say it will help because it will mean more scientists working on the same problem and more investment in the same problem. And physicists usually are fairly collaborative people by nature. And that more money, more training. I mean, if there's a bunch of work going into building the quantum computer in Queensland, for those who don't know, just to step back a little bit, the Australian government recently announced a large investment in building a quantum computer in Queensland. Nearly $1 billion is a combination of grants and stock purchases and loans. So yes, that's what's going on there, and that's a lot of money to pump into the ecosystem, which is great. And yes, one expects that will only help quantum research in Australia, but it is a little early to know for sure, I suppose. And yeah, in terms of specifically as it relates to the Sydney Quantum Research Centre, you'd have to ask them, I'm afraid. Not something I feel equipped to comment on.
All right, so there's a couple about electromagnetism. Is it possible to extract electromagnetism so we can walk through walls? And if so, does that mean we would fall through the floor?
Okay, so taking your question in order, is it possible to extract electromagnetism? Maybe. We don't have any means to do that now or know how that would work. But hey, who knows? And if you could you walk through walls? Yes, but you would fall through the floor first, and you wouldn't be able to walk because you wouldn't be able to push off the floor to move yourself forward. So if you didn't have electromagnetism, well, lots of things would go wrong. Actually, all of the particles in your body would cease to be bound. You'd probably instantly die. Would be what would happen. But if you assume that you mean like your self interactions of electromagnetism are retained, so you remain alive, and just your electromagnetism between your body and the outside world went away, yeah, you wouldn't be able to push off the ground to walk forward. So you would just fall into the center of the earth. Yes, unfortunately.
This is a question that hasn't been asked, but is it a appropriate time to talk about how we can exploit electrons passing through walls to build quantum technologies?
Do you mean quantum tunneling?
Yes, I do.
Yeah, so sure, I can comment on quantum tunneling a little bit. So quantum tunneling is one other weird quantum effect that can occur where because particles are not well defined in space, as I mentioned before, they're sort of smeared out a little bit. You can butt an electron up against a barrier that an electron should not be able to pass through. And because the electron is smeared out in space a little bit, some of it is on the other side of the barrier. Some non-zero small part of the electron exists on the other side of the barrier, which effectively means that there is a small but non-zero chance that the electron is on the other side of the barrier. So a quantum particle can tunnel in that sense from one side of things to another. And yeah, that effect is used in various small scale devices to create different kinds of quantum technology. I don't know. Did you want to say any more about that, Kristen, given you asked the question?
No, I just think it's a very cool effect that
Yeah.
we're able to engineer that and use it for our benefit, because it's a little bit like walking through walls. It's just an electron
Yeah, it's
sort of walking through a wall.
in a fairly limited way.
Yeah. Okay, so there's a question from.
It would be possible, like it's theoretically possible that you can walk through a wall because it's theoretically possible that all of the particles in your body could spontaneously tunnel through the wall. It's just that there's so many particles in your body, and so like all of them would need to tunnel at the same time and retain their state. Like it's just like theoretically possible, but just like so unlikely that it will never occur. But if you keep walking into that wall, there's a non-zero chance you will pass through it.
2025 New Year's resolution,
Yeah.
walk through wall.
Keep walking into that wall.
All right. So Paula's question, you mentioned that we don't fall through a chair because of electromagnetism. Would it be incorrect to say that it is also partially due to other forces, in particular attraction between particles, making materials solid?
Yeah, great question. So it is partially due to other forces, the other ones that I described, but electromagnetism is the main one. When you say attraction between particles making materials solid, that is electromagnetism. The reason the particles bond together in the table is because of electromagnetism. It's the same effect. So, like in a lattice of different atoms, the reason that they're bonded together is because they have opposite charges and they attract each other, or yeah, effects of that nature. So it's all based on the same effect. Inside those atoms, there are other effects going on that are very, very important. The nucleus of the atom has to stay together, and that depends on the strong nuclear interaction. But yeah, the thing you're talking about in terms of particles bonding together, same effect. It does a lot, electromagnetism. It's very, very important. And there's a lot of questions about that one there. I can see a few here. What would happen if you were to reverse the electromagnetic charge in an object or particle? Well, if you reversed electromagnetic charge in everything, then I think nothing would happen, because you would have just like, if every single particle in the universe just swapped positive for negative, then I think that wouldn't make a difference. Don't quote me on that, but there may be some, yeah. But the if you just reversed one object or particle, then the force would reverse. So if you say took all of the nuclei of all of the electrons in your body and made them positively charged instead of negatively charged, that would be very bad for you, because all of the electrons would stop being bound to the nuclei, and the atoms would fall apart, and things would get very bad. So don't do it.
Great.
If you're thinking about it, don't.
Yeah. So some more questions about dark matter and particles. So there's a question about exotic matter. Have heard about exotic matter and was wondering what it is and how it fits into the picture.
Yeah. So exotic matter, I think, is essentially just like an umbrella term for new kinds of matter that are not well understood. So I guess in terms of like, it depends on the specific context that it's being used in, I guess. Like, I think like exotic matter, yeah, it means different things in different contexts, I think, is kind of the best answer that I can give. Sometimes it means new particles, which I guess like dark matter could be a kind of. Sometimes it means like exotic states of matter, like particles that we know about that are formed into interesting kinds of ways. But yeah, broadly speaking, it just means, it means exactly what it says, exotic matter. Yeah, and it's sort of context dependent. That's probably not a very satisfying answer, I'm afraid, but that is the case. It just means different things depending on the context.
Well, Callum says you've ruined his plans for the weekend, given they can't reverse their charge.
Yeah, sorry, Callum. I mean, yeah, and I just don't recommend it.
So there are theories that suggest that there may be 6 types of each particle or boson. Would that include dark matter? So 6 types: matter, antimatter.
Do we mean like the quark, like the 6 quarks? I'm not sure.
Can you see the questions?
I can see the
See
question. The 6 types matter, antimatter of each particle boson. Would this include the dark matter? Yeah, I would say like no. I guess depending on the specific theory that you're talking about, no, because if it's like an antimatter variant of one of the existing bosons or something, then it shouldn't have the properties of dark matter. I will comment that neutrinos kind of are dark matter, for those who are interested in fundamental particles, in that they have some small mass, we think, and they don't really interact very much with things at all. It's just that we know neutrinos are not the dark matter that we observe, because there aren't enough of them to account for all of the dark matter that holds the galaxies together. But yeah, I would say like, yeah, just a matter-antimatter pairing of a standard particle could not account for dark matter, because it would not be expected to behave the way that dark matter does. For what it's worth, if you're talking about like supersymmetry, which is one of the candidates for a grand unified theory, supersymmetry is a physics theory that says that every particle can have a supersymmetric partner particle. So it's like there's matter, antimatter, and then there's the supersymmetric partners, which maybe is the kind of thing you're talking about. The WIMP, dark matter, is actually a prediction of supersymmetry. So in that sense, yes. So it's not like matter, antimatter. It's a different kind of particle that is predicted. And yeah, if supersymmetry is true, that theory, then the particle you expect to exist is what is sometimes called the WIMP, the weakly interacting massive particle. It's also sometimes called a neutralino. And yes, so in that sense, yes, if it was a supersymmetric partner, then maybe.
So Hinza has said, I read somewhere that dark matter behaves as a perfectly ideal fluid at extremely high temperature. What do you say about that?
I say that I don't think that is, like, I guess, behaves in what way. I don't know. I'd have to look at specifically what you're talking about. It doesn't immediately jump out as meaning much to me. Dark matter is, there are different models of dark matter that have different predictions about like how hot it is. Generally speaking, the most common cosmological model is what we call the cold dark matter model. So dark matter is predicted to be fairly cold and moving fairly slowly. And when I say fairly slowly, I mean like 1/1000th of the speed of light. So not like super slowly, but like slowly by particle physics standards. That's the sort of best answer I can give to that. It doesn't immediately jump out to me as meaning anything, but I guess in terms of it behaving that way, it would depend in what way you mean that it behaves that way, like the motion of the dark matter or something. I don't know.
I mean, superfluids are a thing that happen to regular matter at very cold temperatures, right?
Yes, superfluids are a thing that happen to regular matter at very cold temperatures. That's true. Yep.
Something at the opposite end of the spectrum.
Right.
Um,
Superfluidity might occur in dark matter as well, for what it's worth. But yeah, that's a whole other thing.
yeah. So how would you program qubits if you can't observe particles in a superposition?
Yeah, so this is a fairly complicated thing. The answer is about preparing like your qubits in such a way. So this is why, like, I think it's important to highlight that, like, it is not currently really expected that quantum computers will just replace classical computers entirely, because they are good at specific kinds of problems. So, like, there are specific kinds of things that are very hard for classical computers that are good for quantum computers. And that means that there are specific algorithms that are used on quantum computers. So it's about preparing your states in such a way that they collapse into the right answer is sort of like the best answer that I can give you. So you need to prepare them in superpositions and also entangled and working together in such a way that when they are measured, they collapse into the right state. That's effectively it. They stay in superposition until the answer falls out.
Why is it said that Australia punches above its weight regarding quantum research?
Yeah, just because we're a very small country and we do a lot of very good quantum research. It's as similarly to the Olympics, for a relatively small country, we do comparatively well compared to other countries of similar numbers of people. We produce more papers and more patents and more interesting quantum technology. So yeah, be happy with that.
So there's two that are sort of semi-related. One from Jared, how do you see Australia's involvement in dark matter research evolving over the next few years? New experiments, international collaborations.
Cool.
And from Paula, if a photon of light is not detected in the experiments to detect dark matter, what next?
Yeah, cool. So yeah, taking them in order, Jared's question, how do I see Australia's involvement in dark matter evolving over the next few years? Okay, well, the first thing is that the two experiments that I mentioned before will continue to evolve. Sabre will come online, start taking data, and that data will be very interesting because it will either confirm or refute the dark matter signal from this other experiment. So there's this thing I didn't mention, which is that there is an Italian experiment called Dama Libra that claims to have observed dark matter. And they claim to have observed dark matter in a specific way where other experiments have looked in the same way and not seen it. And so it's kind of interesting. I won't go into it too much, but effectively it depends on this thing called annual modulation. So Dharma Libra sees an increase in counts in their detector in one half of the year and a decrease in counts in their detector in the other half of the year, which is something that you would expect for a dark matter detector, because as the Earth orbits the sun, I mentioned before that there was like a wind of dark matter. Half the year we're moving into the wind and half the year we're moving against the wind. So half the year we expect more dark matter counts, half the year less dark matter counts. And Dharma Libra sees this kind of modulation annually. But they don't see like enough counts at any time to say, oh, this is definitely dark matter. Like you always see counts. Like if you turn on one of these experiments, you're going to start getting counts because there's background noise. There's those cosmic rays I mentioned. There's stray light events. There's also just these things called dark counts where the detectors just randomly go off even though there's no signal. So there's like background noise. So you always see counts. You need to see a large number of counts above the expected background before you can claim that you've observed dark matter. That's called signal to noise. And what Dharma Libra sees is they don't see a statistically significant excess of counts. They see their background count rate modulating. And they say, this is dark matter. And other people say, no, we looked there in that way and we didn't see it. And they keep saying, well, we're still seeing the modulation. And so Saber is like the obvious thing that you can say though is like lots of things vary annually. Like the season varies annually, and maybe the slight variations in temperature interact with the detector in such a way that they cause more counts and less counts. Or maybe it changes the thickness of the atmosphere a little bit, and the muons, those high energy particles from space, maybe there's more or less of them at different times of year. So one way to determine whether it's a seasonal effect or whether it is truly dark matter is to build the same experiment or a similar experiment in the Southern Hemisphere, which is what Saber is all about. It's following up on this Dharma Libra experiment in the Southern Hemisphere. So it will either see the same signal, in which case we will all say, oh, damn, they really did detect dark matter. And that would be really awesome. Game over, we all go home. No, not really, but that would just be the beginning of research, but it would be like a huge discovery. Or they won't see it, and then they refute that experiment, and then that would be a big contribution internationally. In terms of other international collaborations, on the axion side of things, away from the WIMP dark matter side, then there will be there is a major international collaboration working on axion detection that is called the Axion Dark Matter Experiment, and it's based largely in the United States. And Australia is taking an increasing role in this collaboration as well. So the University of Western Australia is a node of that collaboration, and Swinburne University, where I work, has just become a node of that collaboration as well. So we are becoming more involved in this big international search in addition to hosting our own searches. So that's really great. And yeah, I mean, in the next few years, I certainly hope that there are more new experiments and new collaborations. I'm building some new experiments at Swinburne at the moment. So yeah, hopefully build more and collaborate more for sure.
And then to Paula's question,
yes, love that question, Paula. Thank you. Well, then we will move on. So the short answer is okay. Well, the short answer is we will move on to other models of dark matter. The long answer is another thing that I didn't mention, just for time and clarity, is that like when you build an axion detector, you aren't sensitive to like all concepts of axions. So one of the biggest problems in doing dark matter detection research is that we don't know the mass of the dark matter particle. We know how much dark matter there is overall. We know in every cubic centimeter of space, there's about half a proton's worth of mass, or about 0.45 giga-electron volts, if you're that way inclined, for every cubic centimeter of space around us. But we don't know whether that's made up of a small number of heavy things or a large number of very small things. And so say an axion detector, for example, when you build it, you have to build it sensitive to a certain range of axion masses. So when we build these experiments, we say, okay, we're sensitive to these axion masses. And if you don't see a flash of light, you say, okay, the axion does not exist in this mass window, and you move to the next mass window. And you do that for quite a while until you were reasonably confident that you'd exhausted all of the mass windows for axions, and then you would say, okay, I guess the axions aren't the dark matter. But we're not there yet. Like, these experiments have only really started to get good in the last decade. So we're nowhere near having ruled any of these things out completely. just yet. But if they are ruled out completely, then yeah, I mean, if we're good scientists, we wouldn't play favorites with our experiments. The idea would be that you move on and you look at other candidates. And again, I've mentioned too, there are lots of different candidates for dark matter. And as I said before, that is the way science works. You do more wrong experiments than right ones. That's just what happens. When you're trying to do discovery science, the vast majority of experiments fail until one discovers something completely revolutionary. So you almost expect to not find anything and hope that you do.
All right, we're getting towards the end, but we've got 3 more questions.
Great.
So would it be possible to detect dark matter through its drag, as in the famous ether drag experiment done in the 1990s to disprove the ether? And if not, would you be able to detect the wind?
Right. Okay. So the first question about drag, that's a really cool question. And the short answer, well, no, I won't say short answer because I don't know how long it's going to take me to say. Like, yeah, kind of. There's a proposal for an experiment that does this. It's called wind chime. The idea is that the drag would be gravitational drag. So again, like the one thing we know about dark matter is that it interacts gravitationally. It won't have drag in the traditional sense because that comes from electromagnetism. The reason that like a car creates drag is because it's interacting electromagnetically with like the wind particles. But dark matter won't do that. But it will create gravitational drag. As a dark matter particle moves through, it has some mass, it interacts gravitationally, it pulls a little bit on everything around it and leaves kind of a gravitational wake, which in principle you can detect. And that experiment would be completely agnostic to what the dark matter is, just that it has some mass and that it's moving past us. So yeah, short answer, yes. And it's just really hard because the problem is that gravitation is the weakest of the fundamental interactions. It's so weak compared to electromagnetism or strong nuclear or whatever that we just can't really like detect gravity on that scale, like the gravity trail left by an individual particle. But that is something that quantum sensing might help with as well. You get those sensors more and more advanced and you can measure very, very, very tiny changes in gravity, then maybe you could detect gravitational drag like that. So yeah, there is a project that is trying to do just that.
Great. Is it possible that dark matter doesn't exist and the gravitational forces that have been picked up are just normal matter that doesn't get picked up by sensors?
Right. So some kind of dark matter, perhaps. Yeah, I mean, in a sense, like, yes, but that's sort of also like that's kind of the hypothesis that it like I guess it's what's the difference between dark matter and normal matter that doesn't get picked up by sensors? Normal matter is dark matter is just matter that doesn't interact with light. So if it's just matter that you can't see with a telescope, then it would be dark matter by its very nature. If what you're asking is what if it's made of something that we already know about? Well, then there would have to be a compelling reason for why we don't see it. Like if it was gas or dust that's like in a galaxy when we can see all of the other gas or dust. But it could also be some exotic form of that matter. And that is also one of the theories. Like one of the candidates for dark matter is this thing called a massive compact halo object. So effectively regular matter, stuff that we understand, clumps together into very small things similar to black holes that are really dense and really small, and we don't see them with our telescopes. And they could explain like the dark matter. It doesn't have to be something new. It's just something that we do know that's existing in a different state so that we can't see it with our telescopes. So yeah, that's one of the hypotheses. People do look for those. The problem is you can't look for them directly because they are so like dense and small and you don't expect them to pass through the laboratory very often. So you look for them with telescopes. And people do look for those with telescopes. They look for things like primordial black holes and other kinds of massive compact halo objects. They are largely, though not entirely, ruled out. So it's possible that it's something like that. It's one of the active candidates, but a lot of the parameter space for those has been searched and not seen. So yeah, could be though. It's one of the things people look at.
Have we found a particle or wave that can go through dark matter?
Yeah, all the regular matter passes right through the dark matter, doesn't interact with it very much at all. So yeah, in a sense, you are a particle or wave that goes through dark matter, or the dark matter goes through you, depending on which viewpoint you take while you look at it.
All right. And to finish off, if electromagnetism suddenly vanished, would the universe collapse? That's from Mark.
Okay. Would it collapse? No, I don't think it would collapse. I think the dark energy would keep driving it apart. Um, Certainly all matter would kind of stop existing the way that it does. Like atoms and stuff would like deform, and yeah, molecules and compounds and all of that stuff would just kind of drift apart under the influence of gravity, or drift together under the influence of gravity, I suppose. But I don't think we would expect the universe to collapse whilst there's so much dark energy in it. Remember that the regular matter that makes up like the stuff that has electromagnetism is like 5% of the stuff. So if you got rid of all that stuff, most of the universe kind of wouldn't care. The dark matter doesn't experience electromagnetism anyway, so it's just going to keep on doing what it's doing.
And someone got one last one in.
Okay.
Could dark matter have different states, e.g. liquid, solid, gas? And if it stays individual or in single particles, waves or particle?
Yeah, to answer the second part of the question, waves or particles, because dark matter exists in our universe, we expect it to be governed by quantum physics, which means this whole time I've been saying particle, I mean a thing that experiences wave-particle duality. So yes, the dark matter is also wavy. Yeah, it's one of the limits on dark matter. So I said before that we don't know the mass of the dark matter particle, and that's true. But we do have like some broad limits on the mass, which is it turns out that the amount of waviness, like how wavy a particle is kind of roughly proportional, like inversely proportional to its mass. And so we know that the dark matter can't be so light that its wave nature is like bigger than the scale of a galaxy, or the dark matter wouldn't fit in a galaxy, which is where we know that it lives. So the dark matter is definitely wave particle, and that's one of the things that limits like how heavy it can be. In terms of could it have different states, liquid, solid, or gas? Maybe. It depends on the interactions that it has. So the reason that regular matter forms those different states is because of combinations of those four fundamental interactions, primarily electromagnetism. The reason that like things group up the way they do is because they're attracted to each other through electromagnetism. So dark matter would need to have some kind of exotic interaction that we don't understand yet for it to interact. One of the things that we suspect about dark matter, if it is something like a WIMP or an axion, is that it doesn't really have much in the way of self-interaction. They just kind of float around. But yeah, very, very much maybe is the answer. It would be some kind of new exotic thing.
All right. Well, thank you very much, Ben. There was a lot of comments saying thank you for an excellent talk. So good job. We will put this recording, this has been recorded, we'll put it somewhere online if anyone wants to come back to it later. You mentioned that you had some links. Would you like to share them, or I can just say them out loud?
Yes, I will put them up. Hang on one moment. Do, 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 do. Do, 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 do. Do, do, do. Oh no. I've jumped to the start of my presentation when I meant to jump to the end. Okay.
Oh no.
Here are the links. Take a look at them if you're interested. qdmroadtrip.org has information about those remaining public events. So there's 2 science trivia nights in Melbourne in the coming weeks. Equus and centredarkmatter.org have information about the 2 centers. We also have some online resources. So at equus.org, you'll find various things, including our very own podcast, Clear as Quantum, which I am not on, but is fantastic and contains many other good researchers. And yeah, if you want to get in touch, you can email Kristen there at comms@equus.org. We'll get on social media at The Road Trip or at me, or you can check out my website and email me through there.
Yeah, there's also pub trivia in Perth tomorrow if you
Hey!
happen to be in Perth.
Nice. Very good.
And there's a demo day in Sydney on Saturday. So if you happen to be in Sydney, Melbourne, or Perth, there are upcoming road trip events. Otherwise, yeah, check out the website and the social medias, as Ben said.
Great.
All right.
All the information is here, qdmroadtrip.org. Yeah. Okay, thanks everybody. Have a good National Science Week.
Yeah, thanks, Ben. Thanks, everyone. See you later. Bye.